I'll try and remember to pause and ask for questions. It doesn't matter if I don't finish my slides, because I want to make sure people are getting something out of the bits I'm covering. There'll be more details on each separate section, I think, as the summer school goes on. So my attempt will be to give you a sort of general introduction and highlight some of the challenges in machine learning and current solutions, and try and describe to you what machine learning is and why it's important, particularly in the context of data science. So we have a lot of buzzwords now: machine learning, data science, artificial intelligence. So I'll try and give you a sense of what I think those buzzwords mean. Okay, so machine learning, in 1996, no one had really heard of it, and now you see it a lot in the press everywhere. So I just want to give you a sense of why that is. So the rise of machine learning, I think, is driven by data and computation. And why I really am excited about Data Science Africa is because of the other component of that, which is also communication. So one thing that I always find amazing here is when you land in, certainly it's been true in Kenya, Uganda, and now Tanzania, you have 4G everywhere you go, certainly in the population centers, very high bandwidth. You know, I've had conversations with Shira where he's operating on 4G from his house via Skype. In the UK, you don't have that coverage. You don't have high bandwidth everywhere. In fact, in my house, my mobile phone doesn't even work. So it's one area where Africa is, in many states or many places, ahead of Europe. And of course, that's because the existing infrastructure doesn't work well. So having, you know, the roads aren't quite as good, and there's not as many trains. There's not, you know, the sort of traditional infrastructure isn't as strong. So there's been a large investment in the information infrastructure. But the information infrastructure is the modern new infrastructure. So the really interesting question for Data Science Africa is, how can you make use of that? Now, machine learning is about bringing these three things together: bringing data together with a model of the way the world works, and using computation to then make a prediction. And that becomes very, very important if your main infrastructure is an information infrastructure. Okay, so this is what I picture of the data revolution. So these lines here, oh, I've lost my mouse. Why don't I move my mouse? There we go. These lines here are meant to represent the bandwidth of communication. So the normal communication between a human and data is quite low bandwidth. If you just try and sit there reading numbers, or how many people remember learning their times tables? You know, that's quite a low bandwidth communication to learn about data. But there's this very high bandwidth communication now between the computer and data. And of course, that's to do with things like the mobile phone, and then of course, Internet of Things. And it's great that we've got, you know, people from ARM here. Jan's a sort of evangelist for the Internet of Things, who'll talk about that. That means that there's this very strong connection now between the computer and data. So you can actually set up things like one of the Global Pulses projects is to actually have speech recognition applying to radio across the whole of Uganda to try and understand when there are health issues or natural disasters in Uganda, and then bringing that data together into one place so that they can analyze this and know how to respond to these things. That's possible because of this high bandwidth connection between data and a computer. You could have humans do that as well, but they would all have to have a human in every place listening to the radio the whole time, so it would be quite expensive. But this high bandwidth means that John can pull all this data together in one place and process it on the computer, and then summarize it to the human. So again, this is a low bandwidth, so the communication rate between the computer and the human is low. So this means that this relationship between the data and the computer and the human is vital. And I would say that's what data science is. It's the mapping of the information from the data via the computer to the human. And it's a new thing because traditionally, statistics was operating the human to data connection directly. Now, statistics is very, very important still at many stages of data science. But classical statistics was about this connection. And data science, I would say, is about this connection. Whether that's about bringing data together, visualizing it, allowing people to see what's going on, or whether that's about doing some modeling on the data. And this phenomenon is everywhere at the moment. Okay, so why does data science become important? It's because of efficiency. It's because economies are driven by production. Trying to increase the GDP of Tanzania or Uganda or Kenya is driven by increasing the efficiency of which we work so that we have to do perhaps less manual labor, right? If you look at mechanization of agriculture, where that happened, that meant people could move from the land to the cities and they had time to do other things. The nature of work changes. And then if we go further back, if we go sort of, 10,000, 15,000 years ago, moving from gathering food in the forest to actually making our own agriculture. Now, in the modern era, one approach to development is becoming efficient, more efficient is automation of processes. So manufacturing production lines, how you make a product with a production line to make it more efficient. But I think where machine learning comes in is that you can do all these things on a physical process like logistics and the supply chain or manufacturing by automating. But typically, you have, in the modern era, flow of information. And modern society, the management of goods and information and this interaction between the two. So is it the Kudu project you have in... So the Kudu project in Uganda is a really interesting example of that, where you want to move goods, agricultural goods, to the correct market where they're demanded. But rather than driving the goods to the market and trying to sell them on site, what the people do with the trucks is they try and organize to sell their goods before they move. So they make a sale to the right market, so they know whether to drive to Kampala or to drive to somewhere else to sell their goods because they know where the demand is. So rather than driving the whole goods there and trying to sell, you move the information first and then move the goods later. Now that's a chance to really make things much more efficient. And you can see how much more important that is if physical infrastructure isn't strong, right? So it's less important if it's easy to move things around physically. It becomes much more important that you find creative ways of doing this when it's not easy to move things around physically, but it's easy to move information. And that's very much the situation that you find yourself in, I believe, in Tanzania. So the typical way that we do that, and even the Kudu project doesn't really involve machine learning, is processing of data. You just decompose the things you need to do in sort of computer code. You write computer software to process information. And that's great. That works very well. That's been behind the software engineering revolution. But typically, a lot of these pipelines require humans to intervene in them. So if we're manufacturing, you can't just put things in the factory and have them come out the other end. Humans are doing all these sort of things that the computers or the machines can't do. Machines are good at repetitive tasks. Once you can set the machine up to do it 1,000 times. But if you need a human to bring the products in, or if they're coming in different packaging, you end up needing humans to do that. Now, machine learning is basically the key technology in automating the equivalent manual stages for information processing. And the way it does that is by looking at data of humans carrying out the process and then basically copying that, emulating the data. So that's why machine learning becomes very important in this data science pipeline. It's certainly not the only aspect of data science. There's issues around data storage, infrastructure. There's issues around visualization and presentation of the data. But where machine learning helps is where you have parts where you've got a process that is an information processing setup, where you typically would have it by a human. And another example, so I'm just very familiar with the UN Global Pulse examples, is where you have, for example, a slide of malaria, right? So you've got a slide which is a blood sample, and it potentially has the malaria parasite in it. And what you typically have to do is have a human look at that slide and determine if there's malaria there, right? So now that's a point at which you can't write a program to say, if there's a plasmodium in here, then declare malaria, because the process of how you determine what a plasmodium is difficult. It's something that humans can learn, but it's not easy for them to sort of describe to a computer and turn into a program. But what you can do with machine learning is you can get a lot of data of slides where there are plasmodiums in, and people have labeled them as such, and slides where there aren't, and then tell the computer, this is the data. And then machine learning develops a function to recreate that mapping for you. It still doesn't know how you did it, But with enough data and with the right technologies, you can replace the human in that step. So then you get the manual processing out, and then you can sort of improve. You don't have to distribute the expertise. You can have the expertise centralized, someone doing that thing centrally in a lab, and then you can distribute the program to every sort of health center in the country. So this is a really amazing way of taking human skills and distributing them. Very powerful. So the interesting thing is that there are challenges, and I think we're not focused so much on the challenges, but in machine learning, if you look at the academic literature, is what I call the long grass. So the long grass is the area where it's difficult to solve things. So some things like, it's not easy to solve this malaria classification example, but it's possible, and you can see at the outset that if you get enough data, it's likely to be possible. But there are there are very many long grass regions where it's difficult to collect enough data to try and recreate the sort of challenges you have. Okay, I think I'll skip through that. Now, this is something, because I work at Amazon now, maybe I'll show this quickly. I think that the sort of things that are going on now, this is something that's running out of Cambridge in, oh no, that's not the right video. Okay, forget that. Let's just have a look. Primary. There we go. So in, oh, that's the one. Oh, no one used the internet for a moment. So this is one of my favorite examples that they have at Amazon of doing this, which is Prime Air, which is drone delivery. So drone delivery, at the moment, actually this is a meeting that I was at where the drone is just delivering, it's just left some sun cream there. It was a nice day in California, but that isn't the one I wanted this one. So drone delivery is an example where these worlds start to interface. So in drone delivery, what you're doing is you've got the ability to move small things with automated drones, which can be a sort of, so you can imagine that these could be medical devices, which is a sort of new infrastructure for physical delivery. Now, why I find this interesting, now these things don't have an enormous range at the moment, so the chances are that you're not going to actually get delivery across the whole of Tanzania with one drone at the moment because these are battery powered. But this is a video from the drone of it delivering to its first location in Cambridge, UK. So this is a guy ordering the thing he wants, which is a Prime Air TV stick and some popcorn. This is the fulfillment center that they have in Cambridge, where this is a development fulfillment center. So in this fulfillment center in Cambridge, they're developing how you would process this. So these are the orders going in. They go into a box, they go into the drone. In this case, the drone is then taken outside on a set of rails, and this process is all automated. So there's interesting questions around this in terms of, you know, what sort of infrastructure can you imagine if you were doing this? So as it says, it's not simulated. This is a real delivery to a customer. This is the first ever delivery to a customer. And I know there's a lot of things here which are about machine learning, so which is about how the drone avoids other things in the air, how the drone makes a safe landing to ensure that there's people not around, and so on and so forth. There's a large number of things around that. That's called sense and avoid technology in Amazon that all use machine learning. But I think the thing I want you to think about in this example is the difference it makes if you can move physical goods like that automatically with a click of the mouse, and over what scale you can move them. And if you have an infrastructure that allows you to do this. So he just had to walk into his garden to pick up that package. His house is very close to the fulfillment center. But he just had to walk into his garden to pick up that package. And I think you can immediately see the implications for things like medicines, which are easy to deliver. And people are certainly looking at that. Now, that's going to make a big difference to the modern infrastructures. And I think that machine learning, we know it's a core part of automating that delivery pipeline. But that's the sort of larger system that we'd like to have to affect these things in practice. Let's see if I can get back to the slides. Oh dear, off my slide. Oh, I know have to go back, don't I? I used the wrong thing. Here we go. Oh, now that's going slow. Okay. Okay, so machine learning is a data-driven technology. So it's replicate processes through the direct use of data, rather than trying to get a person to imagine in their minds exactly how something was done. So you can imagine how a number of things are done using computer programming. If that's the case, you can typically program the process, if you can flowchart it. But what you're trying to do is often emulate a cognitive process from a human. Like, if you describe how you drive and how you avoid objects in the street, it's difficult to describe how you know everything you're doing, how your attention is drawn to the child at the side, how you're balancing all these things. So that's the sort of process that is potentially easier to emulate with machine learning than it is to actually describe straight off. And that's what I think is the revolution in machine learning at the moment. So that goes beyond as well if you look into things like robotics, which is, I would say, a sister study to data science. In that case, you're trying to emulate physical processes. So there are things that humans can do physically that we find it hard to program robots to do directly, even just picking up something like this. I mean, people know about the AlphaGo win. It was quite famous, DeepMind winning AlphaGo. The one thing the computer did not do was pick up the Go pieces. Any human can do that. Any child from the age of about 3 or 4 could probably pick up those pieces. To pick them up well, you have to have some skills. But computers can't accurately pick up these little pieces at the moment, which is, sort of shows how far behind they are. So people are using they're using approaches from machine learning to try and help solve that. But the idea I want to sort of describe in terms of what machine learning is basically you emulate that process with a mathematical function. And the easiest way of trying to show that is with regression problems. So this is a regression problem where we're looking at the pace of the winning marathon time from the Olympics all the way back from 1896 to I think 2000, and we're missing 2016, 2012. This is the London Olympics. So here was a Ugandan runner won, and here was a Kenyan runner that won. I don't know if there's any Tanzanian runners. People correct me if they're wrong. It's an example designed to create tension amongst the attendees. So that's Stephen Kiprotich here. So the idea is this is some data you have, and you want to try and emulate this process, which is a human process. It's just quite a complex one involving running 26 miles, a very complex process, less like the malaria one. And here I'm showing you a function which tries to emulate the process. But here the function is just a constant fit. So that this function is saying it's like the average winning pace of the marathon. Now, you might think that that's not a great fit. I tell you, I've run a marathon and I run it at this pace or something like that, right? So even the average pace here, even these guys here, running marathon faster than most, actually, I think most, I would probably hesitate, I don't want to say this too strongly, most people probably can't run 5K in this room at that speed, 5 kilometers. That's a 20-minute 5K, which is already quite a fast time. Most people run that 5K at about 5 minutes per kilometer. So these people are pretty fast. But this is still clearly not a very good approximation. So what you can do is you can look at other function sets. So there's a linear fit. And what we're looking at is the training error here. So the error we make in trying to fit this model. So that was the training error for just the constant, and this now is the linear, and that gives us a lower training error. But then this 2 basis function here is giving us a lower training error too. So this is a quadratic. So this is trying to model this function, the function of a form that pace is equal to the year squared times some coefficient plus the year times some coefficient plus some offset. So each time we add in a term, this is just saying the pace is equal to some constant, which is set to the average pace. This is saying the pace is equal to some constant plus some change over time times the year. And then so on and so forth. And we can change the nature of the function we use, making it more and more complex. Now, that, simply put, is what you're trying to do in machine learning. So you're trying to convert the process that you have, that you're observing the human doing, into a mathematical function that you can then represent on the computer. And then the key is, and I'm not going to talk so much about that, is how do you find the parameters of that mathematical function? How do you make the choice of mathematical function? How do you decide what the key inputs are? Now, how does this relate to artificial intelligence? Because I think there is a relation between, say, artificial intelligence and data science. And I just want to give you a sense of what that relation is. So data science, I would say, is the field that is emerging because we're producing all this data. Look at all you sitting there producing data. You're all producing data because you've got mobile phones. And whether that data is being stored or not, you are currently producing data in a way that 40 years ago you wouldn't have been producing data. The only data you would have produced is you signed the registration form downstairs, and that shows you were here. And look, more data was just produced there with a photograph. You know, the amount of data we're producing now, there's a film going on. All this stuff that 40 years ago just wouldn't have happened. And this data is just kind of being produced not necessarily with a purpose in mind. It's not necessarily, well, it's to sort of save it, to put on a website or whatever else. But later on, people might want to sort of study how data science in Africa emerged. They want to do data science about data science. So they might want to try and collect all this data that was laid down, not for the reason of studying that, but just out of happenstance. And that's the sort of key issue. That's the key difference in data science, that we're laying down this data not necessarily to care about people's health. So another example from UN Global Pulse is looking at data about how people move from one cell tower to another. So you can look at movement data, like we're producing data, I said by mobile phone. So my cell phone provider knows I'm in Africa, right? They know that I just came from the cell phone tower near Goldcrest Hotel, and they know that I've come here. So they know my movement. And you can take data about that. You can take it, which protects in a way that protects the privacy of just saying, if someone's at one cell phone tower now, which cell phone tower do they move to next? So you can have the data of the pairwise cell phone movement, and that tells you about people movement. And you can use that to study the potential movement of disease, because we are all carrying disease around with us, wherever we are. That's one thing, we mustn't forget that. We all have bacteria in us the whole time, whether we're on top of those bacteria or not. So we carry these things around us, and so the movement of disease follows the movement of people. Now, but we weren't collecting, we didn't give everyone a cell phone to collect data about disease movement. That wasn't the reason. We did it obviously so that people can be on Facebook and saying that they're doing this, or that they saw this, or whatever else. So you're using the data not for the reason it was created, but for another reason. And that's the big difference in data science. In statistics, you would typically, if you wanted to know about the movement of data, about the disease, you would go into a village and you would collect data about it specifically, and you would do it in a rigorous, controlled way, such that you knew the data was high quality. But that's very, very expensive to do, and sometimes impossible to do, to control that trial correctly. So the techniques in data science are the ones where we're not controlling that trial correctly. Now, in artificial intelligence, I would say it's a related field. So for me, they're very closely related because both AI and data science have machine learning as a core component of them. But the artificial intelligence task is quite different. It's much more akin to that malaria task I mentioned earlier, right? So it's not that people are just collecting photographs of malaria plasmodium and sharing them on Facebook and saying, look, there's a malaria, so that you can pick these data up. What you're having to do there is you're having to explicitly collect data. And so that's a different thing. We're not laying down the data without caring about it. We're saying we want to complete this task, which is like an AI-like task. And the best way to complete that task is to collect a load of data from humans doing it and then replicate that. So with AI, it happens to be at the moment that the most advances in AI are occurring in that way. AI is artificial intelligence. It's just creating intelligent things. No one says how you should do that. But it just happens at the moment. A really important way of doing that is collecting data from intelligent things and emulating it with machine learning. So two different, philosophically, if you think about it, approaches to what's going on with data. One is that someone laid out all this data and then they come to you and say, I want to get value out of this data. I want to understand about the world with this data that I happen to have. I wasn't collecting it for this reason, but now I want to use it. So that's like data as raw material. And I think that's the big phenomena in data science. In AI, the phenomena is, I want a machine to do this task. I want a machine to be able to predict malaria, or I want a machine to drive a car. So what I'm going to do is I'm going to get people to drive a car. I'm going to take lots of images of pedestrians, and I'm going to build a pedestrian detector. So I stop running over pedestrians, right? Okay. So I think I covered all that. So I think we sort of split broadly applications of machine learning into data science and artificial intelligence. Now, it's not such a clear separation because you can, of course, use AI techniques in your data science, like that malaria example, where you're trying to get, because data science itself involves humans analyzing data. And some of that analysis you can treat as an AI problem and say, I don't want a human analyzing that data. I want to try and recreate what the human's doing and get a computer to do it. And that's what's going on in the malaria example. Or in the example of the radio, where they actually are doing speech recognition on various different Ugandan dialects to try and extract keywords, which a human can do. Well, I can't. I can't extract the keyword from Ugandan and understand that there's a health issue. But you can write software that does that. Yeah, and Ernest here has, at the front, has a sort of task of sending people out with mobile phones into cassava crops and looking at the cassava leaf and counting whitefly on the leaf. Now, you can get a human to do that, but if there's 300 whitefly, they don't bother. They just say many. You can have easily now, you can have an app to do that counting for them. So that's sort of a little AI task, but within the end goal, which is to collect data about, data science task, which is to understand what the process of cassava crops are. So in classical statistics, the question was formed first and the data would come later. But now in data science, what we're seeing is often we're inspired to ask the questions because the data already exists. So the data is first, the question comes later. And that's very close to something called exploratory data analysis. Exploratory data analysis is a domain that basically said that we should do it this way. Okay. So I know I'm behind because we started late trying to set up the film. I don't know how well the film's moving. But, okay. So what is machine learning then in that, and why does it affect both these things? Well, machine learning is observe the system in practice, acquire data from the system in practice, and emulate its behavior with mathematics. Use a mathematical function. Now, and how do you run that mathematics? Well, you don't get a human to do it. You get that to do on a computer. So that's where computation comes in. Computation comes in a few different places. You've got to understand what the right function is, and you use computation to do that, to fit the function to your data. And you also have computation to make predictions from that in the end. So it's trying to take what we do and turn it into maths, and then in turn turn that into a computer program. Very different from the traditional way of programming a computer. So the design challenge is first of all, where do you put the mathematical function? So you want to do this sort of thing, you've got to decide which part of the process, how is it maths? There's very little around us that looks like maths. And so the thing that I'll try and describe next is decompose machine learning into different areas and show you about how people have used mathematical functions to try and solve those areas. Give you the sort of overview. You're going to hear specifics and you're going to run lab classes on some of those specific areas. But this general overarching principle is in general true. And, there's no rules to start. You don't have to do any of the things I'm about to show you next. They're just sort of ways people have done it. There's no machine learning rules. You mustn't put a mathematical function on that. There's just in the end, does it work or not? So this is the general idea. Very simple, right? Simple but complex. Simple, we're going to build a mathematical function, and we're going to make it match what the humans are doing. But complex, it's like, well, which thing is that humans are doing is the mathematical function. You've got to decompose the task now into something that can look like a mathematical function, something you can get the data about if you're doing AI, or if you're doing data science, you already have the data for. So the first and most widely deployed machine learning technology would be supervised learning. And a particular domain of success has been so-called classification. So that's like the malaria example that I'm sure you'll see more of later, where you've got these images and you want to say, is this a malaria-infected sample or not? That's a classification example. We call this, I mean, there's a number of ways of trying to solve that problem, but the way that we're typically doing it, the easiest thing to do is to collect a lot of annotated data about the problem. So to find someone who understands whether there's malaria in the slide or not and get them to label thousands of slides, and then at the end, once you've done all this labeling, you can make a function that takes an input that is, for example, the image of the, from the microscope, and then you sort of ask it to make the output. So here I've used a dog or cat example, but a more useful example would be malaria or not malaria. If you look at the, so Google now have these image things online for where you can upload your images and they'll tell you what's in the image, whether it's there's animals there or whatever. That's just a massive supervised learning problem. So there was this data set called ImageNet that I'll talk about in a little bit in a moment that was labeled with these many, many thousands of categories and 14 million images, but all done by humans. And then you fit models to it afterwards. So it's a simple idea and it underpins a lot of machine learning. In fact, very often, the best way that you can have to solve your problem is typically to try and work out how it's a classification problem. That's like the #1 way to work out an AI problem. Less so perhaps in data science, but an AI problem is to sort of say, what part of what the human's doing here can I turn into a classification problem? So when people are building driverless cars, one of the things they do is they say, pedestrian detection. That's a classification problem. Is there a pedestrian in this image or not? Okay, there's a further aspect. Where is the pedestrian in the image? Because if you're going to drive the car, you presumably want to know where the pedestrian is in the image. But if it's kind of a classification problem, humans don't really drive around going, is there a pedestrian in the image? Is there a pedestrian in the image? Like that. But we sort of know that that's a facet. And so we say, let's build a classifier to help us do that. And that'll be one component in a driverless car. Similar for the drones. So this is an image of a sort of classification problem. Now here it's a two-dimensional classification. We've got green spots and red spots, and this is our training data. And at the moment, our function says that on this side, things are in the green side, and on this side, things are on the red side. And there's an old algorithm called the perceptron algorithm that says, actually, this is a mistake. So this is currently being classified as green because it's on the left, and it shouldn't be. So we should update our function. So I'm not showing you the math of this, I'm just showing you the general idea. So if you see there was a small move to move it towards that data point, right? To try and take that data point into account. Okay, but also this data point. So move it again towards that data point. Move it towards that data point. Move it again. Keep going. Okay. All these data points until all the data points, but now we went too far, right? So this is the sort of challenge in classification. That now we'll never solve this fully. We'll never solve it 100% because there is no linear decision boundary that can separate these data well. And that's the sort of challenge we face in practice. When you're doing machine learning, you will not, I don't think I know of any example in any interesting data set where your result is 100% correct. Even these things which people are doing very well on, they're sort of 99.9% correct. And so you will always get errors as you start doing this. And in some sense, it's kind of important, we'll come to overfitting in a minute, that you do maintain those errors. So in that case, the function output is a binary value. So before we had the sort of regression example with the pace. But now we've got a binary output example, which is different. Now I haven't described what these inputs are. So this is input 1 and input 2. I haven't even described what this example is. But that just gives you an idea of what's going on in classification. In practice, with the malaria example, you're going to have an image, a high-dimensional image coming in, and your classification, this decision boundary will be occurring in a very high-dimensional space. Makes it more difficult. Maybe I'll just pause there and see if there's any questions so far about the things I've talked about. So I've introduced so far, I've said machine learning is trying to emulate data with mathematical functions. And I've shown a couple of examples. One was actually a regression example, and this is a classification example of supervised learning. I haven't talked about the maths. I haven't talked about how we do this in practice. I'm going to have a little bit on that, but You're going to learn more about that through the summer school. I've talked more about the philosophy. So let's try and take questions now on the philosophy. Yeah. So mapping from the machine learning to the physical movement. So that's a good question, and I think that this is so I'll be doing a talk in the workshop, and my plan is to talk a little bit about these sort of challenges in the workshop. So that's a very interesting problem, is how you make machine learning work in the real world. And the answer is a lot of standard traditional engineering techniques. So I'm moving away from the microphone now, so I'll just try and speak loud. And if you don't know the Wi-Fi code by now, bad luck. So let's take an example from the driverless car example, right? Which is, so I talked about pedestrian detection. So let's just call that PD. It's just one component. Now, the pedestrian detection might also be running in parallel with, okay, like on the road from Kilimanjaro Airport to Arusha, there is a nice line down the middle of the road. Now, I know not all roads have nice lines down, but the way they're doing it at the moment is they have road line detection. So lane detection, they call it. So if you've got the road in California, and Elon Musk has got his car driving along here, they drive on the wrong side of the road there, then it's trying to detect the lane as well. So it's trying to look ahead and say, what's the pedestrian detection? Is there a pedestrian in the road, or where is the lane? So these are two separate components, and they're built separately. And then, of course, there's got to be a system for controlling the steering. There's got to be a system for probably controlling the braking. I don't know how it pieces together. Now, these are being brought together in what I would say is a very traditional systems engineering way. That you decide to run these. You have the camera input on the outside. You have them going into these separate boxes here. This box doesn't really talk to this box until further on there's some way of bringing them together, and that might be another machine learning component that is looking at these things and is trying to learn the right decision in these cases. But it's a separate box. And then this separate box has made a decision about what steering input it has to go into this other box, where that box is being told, which is a control system box, probably a classical control system box saying, you've got to make this steering input now, right? And that's all being done in separate pieces. Now, what fascinates me about that is not how a human is consuming information. So we have this sort of vast amount of information coming in. We don't have separate boxes in our head that have been evolved for 50 million years just waiting for road lines to, we take in a scene with, and if it's not a pedestrian, if it's a goat or if it's a cow or whatever else, we don't go, oh, my pedestrian detection doesn't work, let me freak out. We just take in a scene and we take the whole thing, and then there's a sort of input, output, and some of our reactions are so fast that they cannot be consciously saying, oh, there's a cow coming in from the right. I must now decide what to do. Oh, I'm going to put my foot on the brake. If you see something out the side of your eye coming in like that, you don't even recognize what it is. You're braking before that. And that might be, of course, in these cases, you're going to have radar, right, as well. So you've got to try and assimilate that. So this type of design, I call it machine learning systems design, is a new area. It's not a new area to do this component-wise design, but because we've always done that with software. It makes things easier to code, to test, and to write, right? To do it in this decomposed way. But I think that there's really interesting questions that arise when you're putting in components that are machine learning components. And so I think that's a really good question, and we don't quite know the full answers yet about how that will be done in practice. But what you do want to make sure is that when you are designing these systems, you do have a really good characterization of the different parts and great ways of testing them individually and testing the whole thing. Because if you decide to change one of these parts, it will have an effect on the wider system. And I think that's a really important aspect of deploying machine learning in the real world. Okay, you can get your access point back now. Other questions? Yeah, that's a really good question. How can you collect the mobile data, for example, or any data? And this is a major challenge for machine learning at the moment. Oh dear. Seem to have lost the projector somehow. Sorry. Let me just try and unplug this and then answer the question while I do that. Yes, good. So switching things off and switching them on again, standard. Not sure how well it worked with a driverless car. But the question was, how can you collect the data? Really good question. And I personally believe that that is now the major obstacle in machine learning. So machine learning is good and it's nice and it requires some education to do. But I kind of think the tools are getting out there and it's becoming easier to run the software with the right education. And that's what I think is very exciting about doing this here. It's not like old technologies where like I can build a nuclear reactor only in the most advanced economy in the world, you know, in the 1950s. You can build machine learning systems here today and you've got the cloud and everything else. That's great. And we can also teach how to do it. But getting data is the key, is super difficult. So another example from working with UN Global Policies was a student of mine, Ricardo, working with a student of John Martin's on trying to understand malaria prediction, taking in what's called HMIS data, which is health data that's publicly available, and trying to predict where malaria was across the country. And that was great. I don't know if it's publicly available, but we had a contact that would give us the data. But it didn't work. And it turned out that it didn't work because the data that they were prepared to release is aggregated data. So that's bring several health centers together. And then what was happening, if there was a problem in any one of those health centers' data, like there was missing data, when they aggregated it, you lost whether there was a problem or not. So if there was a missing data or if there was an outlier value and it got added into the other data, that destroyed it. And that made the project basically not work. And it was only when Ricardo went into the UN and could go in and see the data inside the UN and work with Martin, and also the same with Martin, the other student, that they actually got this system to work. So access to data is really, really hard. The mobile phone data, that's coming from companies. And again, it takes a long time to build up a trusted relationship with the company that they're prepared to release it. They're again releasing aggregate data, right? Remember I said that they're releasing data, and John, correct me if I'm wrong on this, but they're releasing data to, not publicly, but to the team that's doing this, that says how to move from one place to the other. And that protects personal privacy, because there's privacy issues here. So the unfortunately non-trivial answer is, yes, there's some publicly available data, but unless you're really close to how it was generated, you will often make mistakes in understanding what was done with it. The malaria example made me think of data associated with the Ebola outbreak in West Africa. So I heard a story, and I don't know the truth of this, but here, let me give a plausible line to the story. I heard a story that people who were analyzing the Ebola outbreak data in the London School of Tropical Hygiene were finding that there was no spatial component. So spatial component to data means that you're seeing outbreaks in a shared space. And that just sounds totally bizarre for Ebola because it's a highly contagious, very transmitted disease. Now, the problem we were having with Ricardo and the malaria data is we weren't seeing a spatial component to malaria data that we expected to be there. The spatial component there is because mosquitoes will tend to collect in the same area, and if people have malaria, then it will be transmitted more. But there's likely to be less spatial component with malaria than Ebola. Now, if they weren't seeing an Ebola spatial component, I personally don't believe it was because there's no spatial component in Ebola. I personally believe it's because they weren't in Africa collecting the data. They were seeing data from 1,000 miles away, and the data was bad in some way, in ways that they couldn't even imagine because they hadn't been there and seen the data. So it is not going to work. It absolutely is not going to work for people from the outside to come in and say, we're going to solve all these problems here locally by looking at your data from 1,000 miles away, because they don't understand the issues, they don't understand the problems in terms of how the data was collected. So I think you can be most successful by being very close to the problem, close to the domain, and acquiring the data yourself. But of course, that means it's harder to sort of get started. So how do you get started? Well, the standard problems you can look at. So is your malaria data available, John? Is that available yet? So, and I think that that's something that this community can do, actually. So, not the malaria data. Sorry, the malaria image data. Yeah. So, So that's an interesting. So, John misunderstood meaning the malaria. Sorry, because we were just talking about the other. Malaria. So, the malaria image data, John can make that available for you, and you can try your own methods on that, right? So that's the malaria image of classifying the malaria. But that's different from the malaria data from the health centers, because people don't want to release that because of privacy. So they won't make that directly available, but they can make it available in a reduced form. So it's a long answer because that's just such an important question. These two, actually, ironically, these two questions were the things I was going to talk about mainly at the workshop, because I kind of feel that, sure, we're going to learn about the technology behind machine learning and everything else, but we're getting to the point where we know how to do a lot of these things. What we don't have is great methods of sharing data. What we don't have is a really great understanding of how you put a complex system together involving lots of machine learning parts, and how you operate that and maintain that in practice. Those are the emerging areas. Other questions? Well, let's go here first. How do you secure it? Oh, your own data. Yeah, no, that's interesting. So I don't know the situation in Tanzanian law, but you're worried about your personal privacy with respect to that data. Yeah. So there's typically a lot of controls on what telecoms companies are allowed to do with that data. So it depends country to country what's going on. But there's complex interactions between large companies like that and governments in terms of asking the data for security reasons. I mean, just stepping back, if you look at, say, European law on this, European law has, I don't know what the equivalent legal framework is locally, but European law does this. It says you have a right to privacy, and it describes that. It's like Article 10, I think, of the European Convention on Human Rights, and it describes what that means. And it means that, you know, that they should not be sharing your data. And this is something important to remember when you're working with data that is personally sensitive. You are under an obligation not to disclose things about the individual you're working on. And data science isn't enough of a profession yet for us to talk about these things formally, but I think that that's important. So those companies are under those obligations. Now, they're under those obligations, but those rights are so-called limited. So a limit on rights is the right is there, but it can't be taken beyond. So, for example, we have freedom rights, yeah? I'm allowed to walk around and you can't stop me doing things. But if you commit crimes, then they put you in jail. You sort of forfeit those rights. So there are limitations on privacy rights, which are associated with security. So that's a really tricky area because, you know, when you have things like terrorism and things like this, they can obviously use that data to try and track. And you see a lot of public cases discussing that with big technology firms at the moment. So it's a sort of interesting area. There's two parts to it. One is that company has a duty of care. Two is that the duty of care is limited by the government's ability to sort of ask for specific information for security purposes. And of course, security, you know, we know governments can abuse that, yeah, so it's difficult. Yeah. There was another question, I think, yeah. Yeah, no, I think that it's true. So these are general. So the question was, it seems similar to the statistics and the AI. What's going on in terms of asking the question first and collecting the data, and that's true. It's a good point. The differentiator I was making was with data science, but yeah, that's an excellent point. AI is looking quite different, quite similar to statistics now, isn't it? So, you know, I think in the same, at some point, everything is just maths and data, right? So my general definition of machine learning could be applied to physics, maths and data, yeah. You know, maths obviously has less data, but more maths. So the philosophical difference between AI and stats is probably mainly historically, but I think this will change. And these aren't clear definitions. I'm just trying to give you a sense of the landscape. Is that in statistics, you typically look for explanatory reasoning for what's going on. So in AI, you might want that as an additional thing, but certainly when we're doing the say malaria classification example, we don't necessarily have an ability at the end to say why it's making that classification. You might, but you're far more concerned with the predictive qualities of the model than the explanation power of the model. And it seems that there's this tension between the ability to explain and the ability to predict, because the sort of complex models we use in modern machine learning are difficult to understand exactly the methods by which they're causing a particular outcome. Whereas statistics focused on simpler models such that it could say, such that you could go to the minister and tell him why you think, right? So this becomes really important and interesting in the domain of data science, AI, and stats, and it's big open questions. We're hitting all the big open questions. Now, in terms of if you start deploying these systems more and more widely, and then you need to explain to the Minister of Health why you're choosing to do this based on the back of the AI algorithm, then it's not easy unless you have a good understanding of classical statistics. So you can imagine starting to do weird things like having two models. One is the model you use for prediction, and then you could do classical statistics on that model to try and explain how that model is working. Because if we just step back and look at what classical statistics does, it doesn't say when it's trying to look at disease. So we can go around Tanzania trying to understand malaria, and we can measure things like the altitude, the amount of rainfall. We can measure the local level of poverty in various ways, various indexes we can make up for doing this, right? And then we can go to the Ministry of Health and say, well, in determining malaria, the most important thing is altitude and rainfall, or whatever it turns out to be, right? In that simple way. The way we do that is with so-called linear models, trying to decompose the influence into these different parts. Of course, it's not really happening like that. The mosquito isn't going, what's the local rainfall? Oh, it's 7. And what's the altitude? It's 6. Let me give this person malaria, right? The actual system that's going on is way, way, way more complicated than that. And the statistics model is a summary which is interpretable. So you can see that happening at another level. If you were using a very complex machine learning model, it would kind of be like the mosquito's perspective. Lots and lots of things are going on to show these things are true. But you can imagine doing statistics on top of that that just tries to give you the trend. And that's a phenomenon that's going on now in machine learning. It's called interpretable machine learning, where you try and look at the model and its ability to predict in certain areas and try and explain why it's doing what. So a long answer to the question, which I think was more about what the difference between AI and stat. But I like to try and think about the differences personally, but then I like to try and think about the strengths of these areas and why they all need to operate together and why you need access and people talking together about them. So they interact in a positive way, I think. Other questions? No more other questions? Right, I'm going to start again. Okay. So classification, I mean, it's all over the place. So Amazon now sells this intelligent speaker, which you say Alexa to it, and then it wakes up and answers questions. When you say Alexa, it does wake word classification. It's listening to things, and it's trying to classify if you've said Alexa. So it's constantly listening in the background, trying to see if you've said Alexa or not. It's not doing anything more than that. It's not trying to understand what you're saying until it hears Alexa, and then it wakes up and starts actually trying to understand what you're saying. So that's a good example of it. Major breakthrough for images was this 2012 paper, this ImageNet result that sort of relaunched this big revolution in deep learning techniques that is meaning that we're really getting great results on image classification. This has really changed, it's not changed the fundamentals of machine learning in terms of the challenges, but it's changed massively the number of domains it's deployable to, including things like the way you do driverless cars, the malaria pipeline, the malaria classification pipeline that John has. And that was based on ImageNet, which was 14 million images. So there was a question about data earlier. So the ImageNet thing is publicly available. 14 million images with thousands of different classes that you can then try and train your classifier on. And that was all labeled by human. So it was sort of labeled on Mechanical Turk, this Amazon service for annotation, for crowd-based annotation, by, I don't know, thousands and thousands of people labeled these images. So it's a lot of work to get that data. But once you've got all that data, then you can potentially emulate it. So that's the sort of AI challenge. So a little bit of maths about what's going on. So mathematically, I would tend to talk about those input images or the whatever we've got as X, and then the output, which is a sort of yes or no, is it malaria or not, as Y, and W is the parameters. So W is, you know, the weightings that you're using on the different inputs. Now, what I then call F is I call it the prediction function. I don't know what other people call it. I'm not sure people talk about the fact that it's there so much. But I think it's critical. There's two critical components in what you're doing, and one is the prediction function. This is the function you're using to emulate the human process. So the human takes X in and says Y, right? And so the human, you know, a mathematician views just the human with what they're doing there as a function. That it's taken X in and giving out Y. The assumption, it has to be a function, you have to give the same Y out every time you have an X in. And then it's a function. And so that's the prediction function that you're trying to represent mathematically. And then the trick is, well, there's a few different tricks now. So the challenges are choosing what are the features that the human is triggering on, X. Which inputs were they? So it's not always clear. Sometimes in statistics, as we were just talking about explanatory variables, you might decide that these certain things are relevant. But in general, it might not be clear what the input features are. And that's known as the feature selection challenge. Defining the appropriate class of function. What type of function should one use? And that, I would say, is the modeling challenge. And then, once you've got the right function, you can see it, right? Like, this is just everything on the right-hand side. F, X, and W, 3 challenges. Selecting the right parameters. And that's the model fitting challenge, right? So there's some interaction between these two, but I would see them as sort of separate. You can make separate decisions about them. Because I can choose the class of functions, I can, but I might have the wrong data, the wrong inputs. I can choose, well, I don't know what the parameters are even before I've seen the class of function, but the right parameters are dependent on what the outputs are. So these are the three sort of major challenges we face when we're building supervised learning. So, for example, for feature selection, the Olympic prediction example, we're only using the year to predict the pace, right? So at the moment, we're just saying, oh, here's the year, so we're just going to predict, people are getting slightly faster. But in practice, you might know something about the course. You might know if it was hilly. You might know the temperature at which people were running. You might know if the runner was Kenyan or not. The Kenyans are nodding. And all that will help tell how fast they run, right? So there was one outlier in 1904, I think it was, which was when the race was run in St. Louis, and the runners actually got lost, and they got dust, and so it was much slower. So you might want to know whether the runners got lost, right? You might not want to pay very much attention to that. But which ones should you include? Well, you look at feature selection algorithms for doing that. Automate the process of finding the features we need, right? And then that actually becomes where AI can come back in, because often it's humans that decide this, but now we maybe want computers to do that decision-making for us. And so is that a data science or an AI challenge? Other applications, so ranking search results. When you search in Google, that's being done. I'm not sure that ranking of search results is so much being done by classification there, but certainly the adverts you see on the side is being done by a classifier. Being done by a classifier matching your search term to the sort of terms that people have, your likelihood to click on those search terms given what you searched for. Give it your likelihood to click on particular adverts. And that's true also in Facebook. So in terms of the news feed, when you see on Facebook, that's being done by classification. They're trying to, I think, maximize the probability of click or share, and then they're deciding to put the things at the top of your news feed that they believe you're likely to click on. And then they have to do a feature selection, and I think the sort of features they look at is how many likes that post already has. How many times you've interacted with that person before, whether that thing has an interesting image in it or whether it's got an interesting link. And all those things are, try it next time on Facebook. Try posting something which is just a one-liner with no image and see how many likes it gets, or check with your friends how high it goes up their feed. If you put an image on, it will always push things higher up the feed because they know that people interact with images more than text. And of course, the newsfeed ranking algorithm is critical to Facebook's success in terms of it draws you in and makes you interested in engaging with the site. And the more you engage with the site, the more they can advertise to you. And they've made big investments in machine learning pipelines for evaluating different feature utilities. So they have something called FB Learner, which is all about trying new features and testing whether this helps in predicting whether people like the ads or the newsfeed. Okay, so the class of function, what should be the characteristics of the mapping between x and y? So the example I've shown you so far, I showed you polynomial things, which is sort of initially linear and then quadratic, and then I showed you a straight line classification, which turns out to be a linear function. Now linear is quite often used and very widely used in statistics because it's very interpretable. If you've got linear, then you have a weighted sum of effects. And if you understand something about what those effects are, then this gives you interpretability. So you'll see linear being used a lot for explanation of what's going on. But it's often not so strong on predictive. So if you're trying to make a prediction about what's going on in the system, people typically go non-linear functions. But the sort of things is we choose them to be is smooth. So what do I mean by smooth? So a smooth function is one where similar inputs lead to similar outputs. So a smooth function would be something like this. So if you look at very similar inputs to the function, then they have the same sort of output, right? So that's what I mean by smoothness. People have different senses of what they mean by smoothness. So anywhere I look at two similar inputs, so that's input 1, input 2, they lead to about the same output. Not always exactly the same over here. It's slightly more different than over here, but roughly, ballpark the same. If I look at different outputs, then they lead to different inputs. So it's a smooth function. Now, a function like this isn't smooth. It's got a discontinuity. Now, discontinuities certainly exist. Anyone who's walked into a wall knows that discontinuities exist. But often we don't. If you believe they exist everywhere, then it's crazy, right? It means that you can't predict anything because things move around. What you get then is what we would call noise. So just this all the time. There's no predictability. Now, that may exist to some component in your problem, but you're actually trying to remove it. So very often what you're interested in is this, which is what you would think of as the signal, and then the totally random discontinuous part you would think of as noise, right? You would think of a thing that's corrupting the signal. Now, I mean, the challenge is when you want to introduce discontinuities because it is valid to introduce them at certain times. But that's what I mean by smooth. Now the linear function for interpretability, and then forecasting, we might want a periodic function. So what happens if we're trying to forecast, if you work, for example, for a large internet e-commerce company, and you're interested in forecasting sales? Well, it turns out that these things are periodic on multiple time frames. So you have different weeks, and within the weeks you have some period that will look the same across every week. So you've got some periodic component like that. Across the year, people will buy difference according to the things at different times. So they might buy more in the summer, less in the winter. And then you have things like, you know, people will buy on the run into Christmas. They'll buy lots of things, and, you know, so on and so forth. My birthday, everyone should buy a lot of stuff. So these are the sort of things you might include when you're designing your system, but these are sort of seasonal effects, yeah? And so that's the sort of thing you might want to put in your class of functions. Notice I'm not saying how you do that, because that's, you know, a lot. I'm trying to give you the overview. How you do any of these things specifically requires a lot more discussion on each one. Neural networks, why have they been successful? Well, the convolutional neural networks that people use in image classification, they are including things like invariances in the images. So what's an invariance? Look at this. Look at me. I'm here now, and I'm Neil, and over here now, I'm Neil, right? That's an invariance. It's a translation invariance. And if I do this, that's a rotation invariant. I stay Neil, whatever I do, right? So when you're looking at images, you want to encode that. The computer doesn't know that. The computer doesn't have a sort of sense of, oh, people move around. The convolutional neural network encodes that for you. So those structures, they have these deep structures, which I'm not going to have time to go through, but these deep structures, they're about encoding those invariances, and that's what means they work in practice. That's what means you get a very good performance from them, because they include knowledge you have about the system. So the class of function, if you know about an invariance, these are not easy to include, by the way, invariances. That's why it took a while to get them functioning properly, because they're not easy to include a rotation invariance in an image. And they don't even include full rotation invariances in those images. They're being included in a sort of partial way. Part of it is learned. Yeah, I was just saying that. So in the Olympic marathon fit, we were using functions of this form. So that was a regression challenge where we were weighting different parts. So the input was one input feature, X, which was the year of the Olympics. And then we were creating nonlinearities by putting it through basis functions. And basis functions is a great way to do that. Time-wise, I'm already behind. So I'm not going to say, yes. I'm just going to move on to parameter estimation. So that's all very well, but once we've got the features that we choose, and once we've got the class of functions we want to use, then we've got to work out what those parameters should be, the W's. So when we're looking at this thing here, what should the weightings of these different components be? Now, parameter estimation is done typically by specifying an objective function. So the objective function, sometimes called a cost function or an error function, or in some domains it's called a fitness function or a risk function, is this thing you want to typically, I'd say, minimize. Sometimes you think of it as maximizing, but in optimization we normally talk about minimization. So we want to minimize. So the objective function takes in various parts. It takes in your prediction function, and it takes in your label. And the prediction function, I've left it off here, sorry, it should say semicolon W, has the W's in it. So this is what we think of as the objective or the error function, which is measuring the mismatch between your observed labels and the predictions you're making. And this is typically what an objective function does, and associates a cost with that. So here the cost is quadratic. So here you're saying, at a given year, I'm making a prediction of a pace of 3.5 minutes per kilometer, but the actual observed pace was 3.45. So what you say is you try and minimize this error or objective function. So those are the two primary functions you come across, I'd say, in machine learning: the objective function or the cost function, the error function, whatever you want to call it, and the prediction function. Yeah? And you find the parameters by optimizing this function. So optimizing means reducing, minimizing in this case. So a lot of the computation that you'll hear about that goes into training these models is typically from that sort of optimization. For a classic linear model, then it's pretty fast. You do these things with one step. But for these neural network models, this optimization challenge is a mess because you get a very large number of parameters and they're living in a high dimensional space and they interact in very complex ways. So one of the big challenges is improving the speed of optimization. And it's typically in machine learning, we'd call that the training step. Once you've done the training, making a prediction from a new point with the parameters you've learned, that's called a sort of test prediction. For some reason in neural networks, it's now called inference, which is weird because it's not really inference. But I call it prediction. Okay. So the data is provided typically as a number of points. So we might have n data points. So each of these would be an image coming from the sort of the unlabeled images of the malaria. And then each image has a label associated with it. Is it got the plasmodium in or not? Right? And those things are going in here. You've chosen your class of functions. You've chosen your data. You've got your y. Everything else is defined apart from the parameters. Parameters which should be in this function here. And then you optimize over those parameters. And that's learning. Right? That's what learning involves. So sometimes the label is cheap to acquire. So if you look at, say, the Facebook newsfeed example, the labels are very cheap to acquire because it's whether you click or not. So every time you click, you're giving them a Y, right? They know the X, they know the features, but every time you click on a post, you're giving them a label, whether that post was positive or not. Same with advert prediction. But of course, if you're trying to emulate an expert medical doctor, then the label could be very expensive to acquire. So we normally have to employ human annotators to label the data if we're trying to do these AI type things. So in ImageNet, this breakthrough deep learning result was annotated using Amazon's Mechanical Turk. So Mechanical Turk is a big framework for earning money by labeling and answering questions about online. And so that's enormous, huge human scale input. And of course, they could do that on Mechanical Turk because recognizing objects in images doesn't require particular expertise. It's not that no human ever got it wrong, but you don't need particular expertise to do it. If you were trying to do a medical example, you need expert doctors. And what you'll often find when you work with health professionals is they'll tell you they have the data. As soon as they say that, don't believe them. They may believe that they have the data, but they don't have it in a form that's usable, that is consistent. You know, they may think that they're recording. What do they mean? They might mean that they're recording notes down, right? But those notes don't give us the direct label. And then you get from one doctor to another doctor, you'll get a lot of subjectivity coming in on the diagnosis. So you have to deal with that type of subjectivity. Otherwise, you're just going to emulate the subjectivity, and you really don't want to do that. So the design and annotation of these systems becomes critical to success. Everything else is important, but this annotation step is really, bad data in is bad prediction out. You know, you can't solve for that. You can do some sort of batch modeling, you can do some things, but if you put bad data in, you'll get bad results out. So some tasks are easier to annotate than others. There's this thing called the Tecator data, which is using infrared spectrum to look at meat samples. It's an old data set from the 90s. In Denmark, they've got a big meat industry, and trying to predict the fat and the water content of meat, so what the status, the quality of meat is. Now, if you do that, then you want to annotate the data. Every single label requires an actual experiment. The actual experiment being to take the piece of meat away and measure the fat quantity and measure the water in it. So, you know, that's not just expertise, it's expertise plus experiment. So you can see that your different problems that you'll face will have these different characteristics. If the data is easy and quick to collect by a normal human, you will be able to get a lot of data. You will have to design how you do that well. But if the data is not, if it requires experiments or anything like that, you know, it can be a mess. Take a lot of time to do. Okay. Where's Dina? We're overrunning a bit. Do we have to worry about coffee and stuff like that? Or right outside. So what do you want me to do? Do you want me to go on a bit more or drone on a bit, ask questions, break up? I'll just overview the other types. I could go very quickly through the other types of area. What do you want? You take a vote. You want to know? Well, let me pause. No, okay, what I'll do then is I'll say this one more thing, which is another really, really important thing. Then we'll take questions, and then we'll see where we are, and I'll briefly mention other techniques to machine learning if I've got time. So the other sort of really, really important thing is the distinction between your training data and your test data. So when you use data for training, so this sort of here, you're using data to fit into this model here. You must not use that data for testing the quality of your result. So you're basically, when you use data for training, if you've got a flexible enough class of functions, you will get down to a 0 error. But that is not going to, if you then, what you have to do is you have to hold data out and say, please make predictions on this data that you've never seen before to try and validate, right? To make sure that the model you've trained is not overconfident, that it's not just predicting on the training data only. It's very easy to get 100% accuracy or zero error on the training data. You just need a class of functions that says, give the answer associated with the nearest data point to come in, right? So a lookup table. All you have to do is, like, if we have images on the malaria example, and I want to get 100% correct on the training data, it's easy. I just have to ask, is this image number 17? And if it is image number 17, give the label of image number 17, right? If not, I don't know what you do. That's called generalization, right? If you have an algorithm like that, well, that's called no generalization. You're basically just saying to give the answer of the thing you've seen before. You're just looking it up in a database, and then you're giving the answer out. You've not learned anything because you haven't generalized, right? So it's very important to check generalization. And you do that by looking at the generalization error. Now, this is the thing about the prediction. So you've got to choose the class of functions that is generalizing well. That's the key point, that you want to have a fundamental class of functions that generalize as well. But then you want to estimate the quality of the generalization error by having some data that you test the model on. So after you've done all your modeling, then you ask on this test data that the model's never seen before, so they're new images, you say, what's the result on these images? And you measure the quality of those results. And if the quality of those results is okay, then you've validated that, you've done something well. But be a little bit careful, because then you also use that for choosing which model to use. So what we could start doing is we sort of say, well, each of you, here's a data set. You go away and you choose your favorite prediction function, and you fit your model to this data, right? And then I don't give you the test data. I hold the test data here. And then you all do it, and you come up with your best thing, and then we test you. So it's a little bit like, you've done all your learning, and now you're in the exam, and I give you, without the labels, the test data points. I ask you to tell me your predictions. Each of you gives me back your predictions. I can now score you according to that test data, right? So what should I do next if I want to get the best model? I can take the person with the best score, right? And I can just choose their model. But weirdly, that's another form of training. So you have to be a bit careful when doing it. It's called so we don't call it, when you're doing that, test data. We call it validation data. So it's another form of training because I've done a little bit more learning. Because it's like me being a machine learning system has chosen to use you as people that are producing prediction functions, and then I'm doing learning by selecting one prediction function. So there's another stage of learning going on top. So that's dangerous too, a little bit more subtle in a dangerous way. So what we typically do is we have a validation set as well, right? So you have a training set, a validation set. You use the validation set to justify your choice of function and everything else, and do all the things you want to do to get the validation error right. And then all at the end of that, then you do test data. Now there's other techniques I'm not going to go into, like cross-validation, leave one out, cross-validation for achieving the same result. But these are the sort of things you have to worry about in the process. Now what I'm going to do is I'm just going to stop there and take questions. I did have other things to talk about, but we're overrun a bit, and I'll just take questions at that point. To explore, yeah. So, yeah, so the question was the difference between test data and validation data, and it is a bit subtle, and it's very kind of important, so let's go through it again. So in some sense, one could view it as, in the real world, you don't really have test data, that it's just how your system's going to perform out there. So let's start conceptually from that. Let's say that we've just given you a data set, and you know at some time, someone in the future is going to use your model in the real world on data you've never ever seen before, right? So you can now choose to just do whatever you want with that data set. But the sort of thing you might choose to do is, if you were using a neural network, you might choose to split it into a training set and a validation set. And what you would now do, because you don't know which neural network to use, you would try 25 different neural networks and then test them on the validation set. So you would train on the training set and then test them on the validation set. And then you would select the neural network that does best on that validation set. But it won't do as well as that on data in the real world, right? Because to some extent, it may have just got lucky on that validation set. Like, not if you, with a one-off model, it's not likely to get modeled. But let's say you train 1,000 models. One of them is going to get lucky, right? So one of them will perform better, not because it's better, but because the validation set you chose is finite size, and it just got lucky, right? So, you know, if I toss 10 coins and get a number of heads and tails, and ask you to give me the number of heads and tails, some of you will do better than others. But if I select you, it doesn't mean you're better. Because it's random, right? I mean, it's random. I mean, if you choose no heads and 100 tails, then, you know, it's not a good idea. But, you know, you won't, you know, everyone knows it's 50-50 on the coin head, so no one knows what the distribution is. But if you make slightly different predictions, you'll do better. Not because you know more, but just because you got lucky. So when you choose one of these models, some of the models will get lucky. And that luckiness, if you're selecting for it, it won't bear out when you deploy the model in the real world, which is the real test. So when we're doing it in the reason why there's typically, for a machine learner, there's 3 data sets is because we normally finish our algorithm and publish the paper. So the test data is kind of the data we're pretending is coming from the real world, right? So we typically keep that out as well. So we keep the data in 3 parts. And it's probably good practice to have before, you know, if your boss says, I mean, so you do all this modeling, and then you go up, and Jeff Bezos says to you, so will this model do this in the real world? Then you want to be safe and have had a separate piece of data that you've held out and never looked at before. You maybe even kept in a closed box that you tested things on, and that would be the test data, right? So you shouldn't really look at the test data until right at the end, until you finish your entire decision-making process. Whereas the validation data, you can look at it for model selection. So the validation data comes in for model selection or even stopping your optimization, deciding when to stop fitting your optimization and things like that. It can be used for things like that. The training data is what you're minimizing objective functions with respect to directly. Is that clear or not? I don't know. Yeah, you must. Yeah, so if you view it as, let me try and draw a diagram. Let's try and draw a diagram for the sort of model validation process. So you've got this bit of model training, and then once you've trained the model in here, you go around and then you sort of validation. Let's see. Well, you could train multiple models in here. No, I've not drawn the diagram very well. You know, I suppose you could go around training as many different models as you like, selecting. So this whole process. So it's not just training; it's selecting the function class, doing the training, and then once you've done that, you look at that by validation. So it's not just training. Sorry, select a function class, select your features. Everything I said that you have to do is going on in this box. So not just training, everything on here. And then outside the box, so I uncross that, undo that crossing out, or cross out the crossing out. You have the validation set where you're saying, is this process good? right? And then do another one. You could go around in cycles like that. But then around the outside of that, you want to say, well, was this process good, right? Is that everything I did here before I sell it to Shira, make him take it home, then that's the test data. Now, you would expect your training data, your training set to have a much lower error rate than your validation set, but you would also expect your validation set to have a lower error rate than your test set. Now, it won't necessarily work out like that because of stochasticity and practice, particularly for small data sets. If you have 50 million data points in each of these and they're all drawn from the same distribution, it will work out like that. But very often your data budget isn't high enough to do that. And in fact, this process of validating in practice, if you've got small data, you don't do this type of process. You do leave one out, cross-validation, or tenfold cross-validation, things like that. Is that clear? Other questions? Okay, so take the first question first. Guidance on what size of, yeah, that's tricky. So I don't know what people are using in practice. John, you've been training. They use like 10% for validation or something like that? Yeah. Yeah. Mike, did you have a comment on that? So I think the sort of things that Mike's referring to I can talk about a little bit from this slide. So you have to be careful when choosing a validation set according to your task as well, because look at this one, and if I want to do a validation on this, so actually that is not training error I'm realizing on the left, that's some validation error. But I could imagine doing different validations. So if I'm predicting into the future though, if I'm trying to make future predictions, the right thing to do is to leave out a number of points from a validation set at the end. Because one validation I can do is to sort of validate by taking out points in the middle. I could randomly subsample and take out points from the middle. But then I'm actually looking at interpolation on years where Olympics wouldn't have occurred, right? I'm trying to say what was the change between years in Olympic functions, right? And the right result for the right model for that might be different from if I'm trying to predict forward. So if I'm trying to predict forward into future years, I might need to be more conservative on my style of modeling. And in fact, I know in this example, if you validate by taking out the last number of examples, it chooses, I think, a linear fit. And if you validate if you cross-validate by, if I remember correctly, by doing leave one out cross-validation and looking for interpolation, it chooses a quadratic fit. So you'll get different answers from that. But I think that both answers were sort of saying, I mean, there is no definitive answer to this question, how much validation data do I hold out? Because it sort of depends on the amount of data you have available. Here, you've got so little data, you don't really want to leave any of it out. So this would be a classic example where you would use leave one out cross-validation. And what that is train the model 26 times if there's 26 data, each time leaving one data point out, right? And then put it back in and train the model again, but you have to do 26 fits. And then you average over all those fits what their error is on the single point you left out each time. Now, if you've got 1 million data, that means training 1 million models. So you don't do that. You do something like 10-fold cross-validation, where you leave out like 1/10 of the data each time and train the model 10 times. But with a modern neural network, they don't even do that. They just say, I'm going to hold out. The validation set is sometimes called the holdout set as well. I'm going to hold out 10% of the data, train on 90%, and even watch how good my training is by looking at the predictions on those 10%. And if you've got 1 million data, I mean, you can do statistics certainly on the test data to sort of understand how confident you will be about model performance. So it may be that you know how much data to use for the test data because you want to know how confident you want to be on model performance. But yeah, I don't know. If you just look across different papers, you'll see them doing very different things. So, and be careful as well, because if it's a paper about an algorithm, a method, if it's not trying to solve the actual problem, they don't really care about how much they're putting into their training data because they're trying to more evaluate on the test data. So like if John and I have 2 algorithms that we want to compare on, say, the MNIST data, then however they chose to do it for the MNIST data is more about comparing algorithms, less about classifying digits. So I don't know. Not a good answer, because I suppose there isn't a good answer yet. Any other questions? One here. Oh, the ReLUs. Oh, okay. So I mentioned linear, but they're not linear function, they're rectified linear. So the question was, can I talk about why people use ReLUs? So I'm talking as someone who's never used a ReLU. But I kind of know why I think we use them. And it's because in model optimization, so ReLUs are these activation functions people use. So you use these things as sort of, I would call them basis functions, but weighted sums of these to create a function. So you end up with sort of things like the ability to go around like this. And this is what happens in a neural network. Now, number one, if you put enough of these things together, you can approximate any function, which is a good thing, which is why they like to use them. But the reason that they use these over others is that this interesting reason that in neural network fitting, I think that this is the main reason they use them, is that you're looking at gradients through the neural network. And you're trying to optimize by looking at the gradient of the output function, which is a sum of these all over the place. Now, if you use what we used to use with these sigmoidal things, these things only have gradients in this region. And what tends to happen is you get a lot of basis functions that you only ever see gradients here and here, which is 0. So these basis functions never ever change. And the reason they use ReLUs is because 50% of the time, because they've got gradient in one entire half space, they actually have gradients. So you're more likely to use those basis functions and move them around when you do the optimization. So it's this funny characteristic that is, so I gave a simple picture that you're just choosing your prediction function based on what you think is the right thing to do for the data. But in that case, they're choosing a prediction function based on knowing that it will help them fit the model easier, which is the sort of compromise we also have to make, that you can't use any mathematical function, right? Because some you just can't fit. So in practice, yeah, you choose a particular function because you think that that's the right function for the task, but you are also compromising and choosing functions that you can fit. And I'd say that's the main reason they're using ReLUs. There was one more, and then I think we should break. Oh, is it gone? Yeah? Pardon? IoT. Yeah, so that's going to be a great question for Jan. The question was, for IoT, how can you manage the integration of data that's coming from devices? And how can you manage security? Again, we're going really great. I'm really encouraged by the quality of the questions. That is a question for everyone at the moment. And I think the answers aren't easy, but I know that Jan's may talk a little bit about what they're doing for security on ARM devices. Yeah, it depends a lot on circumstances, and it's a big challenge. So I probably don't want to give any, I'm not an expert in it, but you know, the simple thing that you see going on at the moment is push everything up to the cloud, do your analysis in the cloud, and push the results of the analysis back. But that's expensive in terms of battery, that's expensive in terms of latency, that's, there's a number of reasons why that's not the best idea. The challenge is that if you want to distribute computing between the cloud and the device, we don't have great formalisms for that at the moment. And I know that's something people are talking about within Amazon and elsewhere. And I think we'll see that's a big area of change. Not a good answer, but good question. Yeah. Yeah, no, I think that's one of the other barriers, like to machine learning being possible. And if you ask someone, I mean, it's one of the things I say to people, if you're asking someone about their data, it's something you have to explore. So you've got all this data, but if it's deployed over 15,000 IoT devices in people's homes, you know, is it really accessible? What's the battery load of uploading that data? And different companies seem to be doing very different things about when they're choosing to upload their data at the moment. Like I say, Alexa basically, that device, once it hears the wake word, it uploads everything you say and does everything in the cloud. But they just released this thing, AWS Greengrass, which is about, have you seen that, yeah? Which is about pushing back to devices. But Jan and I were talking about that last night, and he hadn't seen it too much yet. And so that's really interesting, because you've got ARM who are building here, who are building embedded devices, worrying about that challenge from the ARM side, and certainly Amazon worries about that challenge from the cloud side. And I think it's not 100% clear how it will all resolve or what the formalism will be, but it's a really, really important area. Okay, I think we should break now, Dina. Yeah. And I don't know, do you want to come up and announce how long the break will be and what it is? Or okay. The program chair and general chair are just discussing. Perfect. Thanks. Great.